Again, it's a rich thing.
What is going on, guys? Welcome back. In today's video, we're going to cover bitwise operators in Python. And this is usually one of those topics that I like to skip when I teach programming, be it in a course, be it in a video, be it in a book. I usually talk about all the other operators, but I usually skip on the bitwise operators because they're too confusing for beginners. So I mentioned that they exist, I mentioned what they're basically used for, but then we just skip them and we proceed with the rest of the beginner fundamental content. And I think this is good because for beginners, actually, bitwise operators are confusing and they're not very useful because they're not going to need them for quite some time. But what happens oftentimes is that people then never learn about them, at least when they watch my content, because we skip that and then we never catch up on it. Maybe we use it in a project, but we don't really cover what bitwise operators are. And because of that, I wanted to make this video where we cover bitwise operators in detail. We talk about how they work, what they do, and then we're also going to talk about where bitwise operators and how they're actually used in, I don't want to say real life, but in real programming. Now, in order to understand bitwise operators, we need to understand the binary system and bits in general. And I'm not going to give you a full tutorial on the binary system here, but we're going to go through a quick example for those of you who don't know about the binary system yet, but I recommend you watch a detailed video on that. Now, let's say we have a number 28. This number is a decimal number, 28, and it can be represented in the binary system using zeros and ones. How is that done? We basically look at powers of 2, and we ask the question of which powers of 2 28 consists of. Now, 28 in this case consists of the next smallest power of 2, which is 16. Then the next smallest power of 2 is 8, so that would be 24. And then the next smallest is 4. This would be 28. And then we have not 2 and not 1, so we ignore them. And this basically means 1, yes for 16, 1, yes for 8, 1, yes for 4, 0, no for 2, and 0, no for 1. Let me give you another example. If we have the number 19, for example, that would be 16. Not plus 8, because 16 plus 8 would already be too much, so just 16. 4 would also be too much, because that would be 20 already. And the next thing is 2. So 16 plus 2 is 18, and then plus 1 is 19, which means that this is going to be 1, because it's a yes for 16. 0, 0, because a no for 8 and a no for 4, and then a 1 and a 1, because yes for 2 and 1. If that is too confusing to you because you think that I didn't explain it well or anything like that, watch a video on the binary system. That is how decimal numbers are represented in the binary system. We have powers of 2. So the bit on the right stands for 1. Then we have 2. Then we have 4, 8, 16, 32, 64, 128, and so on into infinity or towards infinity. And this is how numbers are represented in the binary system. And this is what we're going to use in today's video in order to explain bitwise operators, because bitwise operators, as the name already suggests, are operators that work with the individual bits of the binary representation. So let's say we have a number 1 here. First of all, let me show you how you can look at the binary representation of numbers in Python. If we have number 1 equals 28 and number 2 equals 19, as we had before, what we can do is we can just say print bin of n1, and we can do the same thing here for n2. And if I run this here, you will see down here we get the binary representation. We get 0b as a prefix, and then we get 11100 for 28, and then 10011 for 19, as we saw. Now, if I want to remove the 0b, I can just say start from the second position, like that. And then we only get the binary digits here. So let's just choose some random numbers. Let's go with 23,477 and 36,213, for example. If I now represent these numbers in binary, okay, one is longer than the other, so let's just make this a little bit smaller, maybe 31,000, so that they have the same length. Those are now the two binary representations of these numbers. And what we're going to do with those is we're going to apply bitwise operators. And bitwise operators, this basically means that we apply the logical functions, which we already know, hopefully, at this point, which are AND, OR, XOR, and so on, to the individual bits. So we don't have something like true and true or true and false. We don't have booleans. We apply these operators like AND, OR, XOR, and so on onto the individual bits, and then we get a new number, a new binary number as a result. So if we have 1 and 1, this would result in 1. 0 and 0, this would result in 0. 1 and 1, 1. 0 and 1, 0. So this is what bitwise operators are basically for. We're going to start with a basic AND. And for this, we're just going to say number 3 is going to be N1 and N2. Now we use a single AND symbol. Now if you're coding in Java or C or C++ or C#, you know that if you want to use the equivalent to a Python AND, which is a logical operator, when we have something like true and false, for example, that is a logical operator. If you do that in the other languages, what you do is you use 2 AND symbols here. For the logical operator, we use a single AND symbol here. So this means take the bits of number 1 and take the bits of number 2 and give me the result of the AND function. So I can go ahead and say print binary number 3, and there you go. You can see here that this is the result of applying AND to the individual bits. 1 and 1 is 1. 0, 0, 0. 1, 1, 1. 0 and 1, 0. 1, 0, 0. 1, 1, 1. For those of you who don't know what the AND function is, basically the AND function is only 1 if both inputs are 1, or if there are multiple inputs, if all inputs are 1. So basically 1 and 1 equals 1. Everything else equals 0. That's the basic idea of an AND function. Again, we're going to talk in the end about the use cases. When do we need that? When is this important? We're going to talk about that. For now, we're just going to talk about the basic functionality. If we want to use OR basically says that 0 and 0 is 0. Everything else is 1. So if at least one thing is 1, everything is 1. Or the final result is 1. Which basically means that N1, if I print, let's say N4 is going to be N1 or N2. This is this pipe symbol here. This is the logical, the bitwise OR. So what we do now is we say print bin N4. What we get as a result here is we get, let me just comment that out so it doesn't disturb us. We can see that everywhere where I have at least 1, 1, I get a 1 as a result. So here I have 0, 0. This is why I end up with 0. But everywhere else here I have 1 or either 2 1s or at least 1 1. And we see 1 as a result here. Here we have 2 zeros again. This is why we get 0. And this is the basic OR function. Again, the OR function always returns 1 if at least one element, if at least one bit is set to 1. The final result is going to be 1 as well. Then we have XOR, which is exclusive OR. The name already says what this does. XOR basically says I want to have 1 and 0 or 0 and 1, but I don't want to have 2 zeros or 2 1s. It has to be different. It has to be either or. OR is just OR and XOR is either or. So I cannot have both. It has to be one of them. So 1 XOR, actually this is OR, this is not right. 1 XOR 0 equals 1, and 0 XOR 1 is also 1. Everything else results in 0, which basically means that if the two values are different, we're going to get a 1. So if I say N5 is going to be N1, and then we use this power symbol here, this hat symbol, N1 and N2. This does not mean N to the power of N2. That would be star star. In this case, this means XOR. So N1 XOR N2 is going to be N5, and we're going to say print bin N4. There you go. So that's, or actually N5, sorry. When we run this, let me just comment that out again. You can see here that it has a leading 0 that is not displayed because 1 and 1 is 0. And if the number starts with 0, it's not going to display that. And because of that, we're going to artificially add a 0 just so we have the same length again. There you go. So 1 and 1 is the same, so 0. 0 and 0, same 0. 1, 1 is the same 0. 0 and 1 is different, so a 1. 1 and 0 is different, so a 1. 1, 1 is the same, 0, and so on. You get the idea of a basic XOR. Then we also have a bitwise NOT, or a negation operator. The problem with this one is that it's not actually what you would think of as a bitwise NOT, which is turning all the bits around. It doesn't work like that because we're working with unsigned integers, which means that if you have an integer and you take the negation of that, you're going to get a negative integer, if it's positive, obviously, in the first place. And the representation is not exactly just flipping the bits here. And because of that, this operator is not necessarily what we're going to use or what we want to use if we want to actually negate a bit mask, because I'm going to show you here. Let me just comment this out and let me comment this out. If I take N1 and I negate it with this wave symbol here, this is the bitwise NOT, or at least the negation operator here, and I represent this in binary, you're going to see that this, first of all, it's a negative number, and second of all, if I now remove the first 3 characters, 3 because there's a negative symbol, you can see that it's not actually the negation of the bits. You can see here it is, but here we have the same bits. I mean, that is the same for both numbers, even though I negated it. So this is not actually a bitwise NOT. This is not actually inverting the individual bits. And because of that, we can do it ourselves. So if I know, for example, that my number is going to have 16 bits or whatever amount of bits, I can go ahead and say 0b, which is just an indication that I'm going to now write a binary number in Python, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 ones minus and then whatever number we have. Now, first of all, I don't know how many bits N1 has, so we need to figure that out first before we do anything. Let's run this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, okay, we need to remove 1 bit here, and then we can say minus N1. Let's print the binary result of that and remove the first 2 digits. By doing that, and of course we need to have a leading 0 here. By doing that, we're going to get the exact negation. We get 1 0 0 1 1 0 0 1 1 0 1 0 0 1 and so on. This is an actual negation. Now there are also other ways to do this, but the ordinary wave operator, which is the negation operator in Python, the bitwise NOT, even though it's not really a bitwise NOT, doesn't work like that because it works on signed integers. It goes into the positive and into the negative, and it doesn't work like that. Then we also have shifting. Now shifting is not like AND or XOR or NOT. We're not applying it to the individual bits. We're just shifting the whole number, the whole bits to the left or to the right, which equals basically in the decimal system, which is the same thing as dividing by 2 and multiplying by 2. So if I have shifts here, and if I have a number, let's say my number is, I don't know, 20, for example. If I now say shift the number to the left 1 time, so if I say shift equals 1, and then I print the number, it's going to be 40. And I'm going to explain to you why that is, if you don't know it yet. Because that basically means that we shift all the bits of the number. Let me show you the representation here. So let's copy that. And let's change this to binary. And let's change this to binary as well. You're going to see that what happens here is we're actually shifting the binary bits. So instead of having 1 0 1 0 0, which is 20, we add a zero to it because we shift it to the left, and by shifting it to the left, what happens is that a 0 pops out in the end, and this basically means that take everything times 2. So instead of having a 1 for 16, we now have a 1 for 32. Instead of having a 1 for 4, we now have a 1 for 8, and 32 plus 8 is 40. This is basically how it works. Now, of course, if I say number and then right shift equals 2, which means shifted to the right twice, this will result in 10, and this is going to be basically just 8 and 2, so 1, 0, 1, 0. And this is now going to be in binary representation, so 1, 0, 1, 0. As you can see, this is 10. So shifting to the right and to the left is the same as multiplying and dividing by 2. So let us now get to the interesting part. Where are bitwise operators even used? What can they be used for? And chances are that you have used bitwise operators in some context before without even noticing that you're using bitwise operators because it came intuitively or because you saw in a documentation that you have to write something like that, but you didn't really think about what's happening behind the scenes. And this is especially true if you're not only coding in Python, but in a language like C, for example, because what we oftentimes use bitwise operators for are so-called flags. So flags, basically, for example, for permissions, let's say we have the following system. We have a permission set, and we can set a permission for a user. Is the user allowed to read? Is the user allowed to write? Is the user allowed to execute? Or is the user allowed to change the policy? Now, if the user is allowed to do all these things, the bits are going to be 1, 1, 1, 1. Because yes, 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 yes. Now, if the user is only allowed to read and nothing else, it's going to be 1, 0, 0, 0. Because yes for read and no for everything else. This is a very basic system that we can use. Now, let's say just in a fictional scenario here, I have person 1. And this person shall have certain permissions. The permissions shall be, this person is allowed to read, but not to write, not to execute, and not to change the policy. Then person 2 is going to have the permission to read, write, execute, but not change the policies. Now, maybe I have some sort of system, maybe I have a function. Let's say I want to do something with those two persons together, and I want to check if they are permitted to do something. So let's say together 1 is going to be the result of the permissions. Now, let's say for this system, I want to say you are only allowed to do it if all of you guys have the permission. And this can be true for many more persons, so people. We don't have to have 2 people only. We can also have 5 or 6, and they all have their permissions. Now, if I want to say all of you have to have the certain permission, then I'm going to use a bitwise AND, because in total, I want to have the least permission or the least powerful person I want to have here. So if I have, for example, here person 3, 4, 5, and then I have this person that's allowed to do everything. This person is not allowed to write, but it can execute and read. And this person is allowed to read, write, execute, or read, write, and change the policy only, whatever. Those are the permissions here. And now I want to know, okay, what is the thing that every one of those can do? So what is the least common the least permission that they all have in common? The least powerful permission that they all have in common. What I can do for that is I can say person 1 and person 2 and person 3 and person 4 and person 5. This is going to give me the AND, the bitwise AND of all these permissions, and I'm going to get the least powerful permission that they all have in common. So if I print binary of together 1, I'm going to get, as a result, 1, 0, 0, 0, because that person has the least permissions and every one of them can read. This is what every one of them can do. Now, if this person here, for example, is not allowed to read, the least common or the least permission that they have is nothing. Because yes, this guy can read, but nothing else. And this guy can write and change the policy, but he cannot read. And because of that, if you want to see, if you want to have the permission that they all have in common, what can every one of those people do? It's nothing, because there's nothing that everyone can do. This is what you can use an AND for. And then the other way around, you can also, of course, say, in order to be allowed to do that, at least one of them has to have the permission. So we can say, for example, for some task, for some activity, there has to be one supervisor that has all the permissions, and then they can do whatever they want. But one guy has to have the permission at least. And then we can say together 2 is just going to be person 1 or person 2 or person 3 or person 4, or person 5. And then, of course, if I have all sorts of weak permissions here, so this guy is not allowed to do anything, and this guy is only allowed to read as well, and this guy can do 2 things, but this last guy, for example, can do everything, then the whole group can do everything. So if I print together 2, everyone can do everything. So this is one thing that we can do with bitwise operators, and oftentimes this is probably something that you have encountered in code already. You're going to have a certain flag constant. So for example, let's say I have a system and I want to have the flag neural read, the permission to read. We still have the same system. Neural read would be 0b1000. This is the permission to read. This is only the permission to read. Now neural write would be 0b01000. So only the flag, or just 2 zeros. Only the flag for this particular permission is going to be set to 1. And I can do this for execution as well. So neural exec and neural change. And I'm going to say 0010 and 0001. There you go. Now, oftentimes what we're going to do in C is when we have some, I don't know, some shared memory or some semaphore or something that we want to set certain flags for, certain permissions for, what we do is we set a, we choose these flags and we use a bitwise OR to combine them. Because if I want to say, for example, let's say def my function and I pass a permission to that function, then let's say the function just prints that permission. So it's just going to say bin and permission like that. What I can do is I can say, okay, my function and the permission are I'm allowed to write and I'm also allowed to read, for example. Come on, read. That is what I'm allowed to do. Now, this is an OR, but it's actually an AND in the practical content or in the practical context. This basically means that I'm allowed to write and to read, and if I run this, you're going to see that this prints 1100, which is the permission for writing and reading. And this is not something that I just make up here. This is actually how it works in a lot of libraries, in a lot of frameworks, where you pass these permissions, you use the bitwise OR to combine them into one full permission, and then you can use that to check if someone is allowed to do something using XOR and using AND and using OR and so on. This is what we can do. Now, another interesting thing that we can do with the bitwise XOR operator is we can swap the values of 2 variables without needing a placeholder. So let's say we have a equals 10, b equals 20. Now, of course, in Python, we can do a b equals ba. So that's not a big deal. And in C, we can do swap and all that. But if for whatever reason you decide to do it with bitwise operators, you can do it without a placeholder. Because usually what you do is if you don't have a fancy function or a fancy notation like that, you say C equals A, then A equals B, and then B equals C, because of course you need to have some value that stores A temporarily, then A is B, and then B takes what A was in the first place. Now we can do it with bitwise operators without needing a placeholder, and it works like that. A XOR equals B, so we save into A the result of A XOR B, then B XOR equals A, and A XOR equals B again. Now this might be confusing, but if I now print A and then I print B, you're going to see that we get 20 and 10 even though we started with 10 and 20. The variables are swapped. Now let me explain how this works. If we look at the binary representation of 10, we're going to see that it's 1, 0, 1, 0. Because it's 1 for 8, 0 for 4, 1 for 2, 0 for 1. That's 10. Now we're going to add a leading 0 because for the next one we're going to need 5 positions. Because 20 is 16 plus 4, so 16 yes, 8 no, 4 yes, 2 no, 1 no. Those are the 2 binary representations of this number, of these numbers. What we do now when we take A XOR B, and this is true for all numbers, is we get a binary number that has a 1 in all the positions where A is different from B from a binary perspective. So it is different in this place, so 0 and 1 equals 1, 1 and 0 equals 1, 0 and 1 equals 1, 1 and 0 equals 1, 0, 0 equals 0. So we now have these 4 ones, which indicate that at this position, this position, this position, and this position, A and B were different in the beginning. If I now take that binary number and I XOR it with 20 again, what I get is I get A. Why do I get A? Because if I now take this here, XOR this, I'm going to get the same as the original, because I'm taking the number 20 and I XOR it with this number, and this number has ones in all the positions where the numbers differed in the first place. And whenever I take something, XOR 1, it's going to be the opposite. 0 XOR 1 equals 1, 1 XOR 1 equals 0. So it's going to invert the positions here. And because of that, what I'm going to end up with here is 0, 1, 0, 1, 0, which is A. Now, if I now go ahead and say A is whatever I have in A, XOR B, I do the same thing, because now I have A stored in B, and I still have this number here representing all the positions where A was different from B, and I now apply it to the original value of A, and it's going to give me B automatically, because A XORed with all the positions that were different from A and B will result in B. So this means that I will get 1, 0, 1, 0, 0. There you go. And this is why this works with a simple XOR operation. Now, last but not least, we can also use bitwise operators to check whether a number is even or odd. So let's say we have some number here, and this is just something, and all I have to do in order to see if this number is even is I have to say if some number and 1 results in 0, then the number is even, and otherwise it's odd. So if I run this, you can see that it's odd. If I change this to 8, you're going to see that it's even. Why is this the case? Because I have some number with zeros and ones here, whatever it is, and then I use the AND operation on that. A bunch of zeros and 1, which means that all of this is going to be irrelevant. All we want to know is if this here is 1 or not. And if 1 and 0 is 0, then it's going to be even. If it's 1 in the end, it's going to be odd. So we're just looking at the last bit, basically. And besides that, also what I want to mention is that in a lot of algorithms that are recursive, not recursive, what was it? In logarithmic time, what we do oftentimes is we divide by 2. And in order to do that, oftentimes we don't say x equals x divided by 2, but we just say x is shifted to the right by 1. So this is also something that you will see a couple of times in algorithms. So that's it for today's video. Hope you enjoyed and hope you'll learn something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video, and bye.